And so currently, wastewater is neither collected nor treated. So 80% of global wastewater is released to the environment without adequate treatment. And this is usually not treated because they think it's a burden. And this wastewater is produced by several industries. So we have the energy sector, so we have the cooling water for power plants and processed water for mines, and even petroleum industry has produced wastewater. Industrial processes such as textile, paper, food, etc. And then agriculture and domestic and living. Now, let me begin with the membrane technology part. So what is a membrane? So a membrane, this one, it's a barrier made of synthetic, organic, and inorganic material, which can selectively separate between a fluid, which is either liquid or gas, and its components. So we have here, this is the feed solution. And these blue circles constitute the fluid, which can either be liquid or gas. And these yellow circles are the components or the solute particles. And what the membrane does is this allows the solvent or the fluid to pass through and to remove most of the solute particles. So this material performs separation of certain species by combination of sieving and diffusion mechanisms. So sieving, so this membrane has different sizes. So it will allow, so if the material is bigger than the size of the membrane, then it cannot pass through. If it's smaller, then it can pass through. And diffusion mechanisms. So inside the membrane, there are several porous structures, and this will either allow the diffusion of these particles or will reject these particles. Membranes can separate particles and molecules over a wide particle range and molecular weights. Here are the advantages and disadvantages of membrane filtration. So among the advantages of membrane filtration are the following. So there is no physical separation of contaminants. And there is physical separation of contaminants, and there is no phase change of contaminants. So we don't have to boil water. We don't have to make it into solid. We just have to separate solid and liquids, or solids and gas, or liquids and gas. This process is typically continuous, and there is comparatively low energy utilization. There may be small temperature change, but this is little, so it's insignificant. Membrane filtration also has compact modular design, less or no chemical use, and there is no formation of secondary chemical byproducts. And ultimately, this process can be easily scaled up and expanded for a wider scale application. This process also has disadvantages, definitely. And these include membrane fouling, low membrane lifetime, low selectivity, and relatively high capital and operating costs. These are the reasons why, until now, membrane filtration is still in development. So we are not able to develop a perfect and a totally sustainable and widely applied membrane process. But we'll talk on that later. Now, let me begin with pressure-driven membrane filtration. So we start with the membrane. So the membrane is here. And we start with a feed solution containing suspended solids, colloids, and dissolved solids. So using the membrane, the permeate will the permeate or the liquid or the fluid which goes through the membrane will contain low molecular weight dissolved solids and the liquid. And this can be used for other work or for disposal. However, everything that is rejected by the membrane or which cannot pass through the membrane, like suspended solids, colloids, and dissolved solids, are left in the solution, and this will be concentrated, and this will be used for other purposes. There are different kinds of membranes and membrane processes. So this is already shown earlier. So first, microfiltration. So microfiltration membranes have a pore size of 100 nanometers to 10 micrometers. So this is the largest size of particles, largest size of pores, and this can remove large colloids and bacteria. So using microfiltration processes, this can remove the larger size particles. Let's make this a little bit smaller. And we proceed to ultrafiltration, which has a pore size of 2 to 100 nanometers. This ultrafiltration process can remove macromolecules and proteins. Let's make this even smaller, nanofiltration. And nanofiltration process has membranes have a pore size of 1 to 2 nanometers. And these nanofiltration membranes can remove multivalent salts. Lastly, let's proceed with the smallest or densest membranes available, which is for engineered osmosis, which can remove monovalent salts like sodium chloride in seawater. And one of the processes involved in engineered osmosis is reverse osmosis. And ultimately, this dense and small pored membrane will be able to produce water. Now, there are two kinds of pressure-driven filtration processes. The first one is dead-end filtration, wherein we have this system. This is your membrane, and you have the feed solution poured onto the membrane, and the permeate goes through, and everything which is not passable through the membrane is left on top of the membrane. So all water passes through the membrane and the particles are trapped on or within the membrane structure. The other type of filtration process is cross-flow filtration, wherein you have your membrane here and the feed solution just passes through on top of the membrane. So the feed water passes parallel the membrane surface. And the permeate goes through, and this product water permeates through the membrane, and the concentrated retentate is carries out the particles out of the system. So in, out, and the permeate goes out in a different direction. The retentate may be recirculated back into the feed or will be treated separately.
Riannya mesti karo butuh. Anu pulangnya dikasih telur. Kasawa.
Saya dari Sumatera.
Sorry for the disturbance.
Yes, or can I continue?
Yes, please.
Yes.
Sorry for the disturbance.
Okay. So another picture is this. So static filtration or genetic filtration looks like this. And as time goes by, all these materials will deposit on top of the membrane, and this will affect the filtration process. And eventually, it will just stop. Whereas for the cross-flow filtration or the dynamic filtration, because the feed water runs parallel through the membrane and the permeate goes into the another side, there is no limit on the performance or there is a significantly better performance deposition based on deposition and the filtration process. So this is one of the advantages of cross-flow filtration. Okay, so these are some of the considerations that we need to do or to consider in designing a pressure-driven filtration process. So we want high flux or high permeability of water through the membrane. We also want high membrane area to volume ratio, which allows low pressure drop while maintaining high flow velocity. We also want back flushing to be possible. Why? Because of membrane filtration processes often involves fouling. So if back flush is possible, then we can eliminate some of the foulants deposited on the membrane surface. We also want the process to be simple and easily installed. And this process should also be continuous and without intense supervision. These processes should also be easily maintained, and the membrane should be simply replaced. Of course, a while ago, I mentioned that these membrane processes have relatively high costs. But then, this is one of the considerations which we need to do. We need to have a process which has low capital costs, so it can be applied for different areas and different countries, even with those with budget considerations. And we also want a process which has a relatively low energy consumption and suitable operating pressure. Now let me begin with the biggest type of membranes available, which is microfiltration, which is a simple screening mechanism process. So this removes the larger size particles. So the microfiltration membranes have, as I mentioned earlier, 0.01 micrometers to 10 micrometers, or maybe around 100. And this is a low pressure process, which involves around 0.01 to 0.5 megapascal. So that's around 5 bar pressure applied. So this is the most effective way to remove particles or larger size particles and microorganisms. This process has a high flux. And however, colloids and macromolar substances can theoretically pass through the membrane because, colloids, these are suspended particles. So some of these particles can be smaller than this size, and thus this can pass through. So microfiltration can be applied either cross-flow or dead-end filtration, and it can be applied using any membrane configuration, flat sheet, hollow fiber, anything. This process needs back flushing and air scoring, or just removing the foulants using water flushing or by air. This process can be automated, and this is a good pretreatment process for reverse osmosis or nanofiltration. Okay. Now, let's proceed to the smaller membrane, which is ultrafiltration. So this process is involving screening and adsorption. And the size of the pores are smaller, and the pressure applied is slightly higher than microfiltration. So this involves 0.1 to 1 megapascal, or that's around 1 to 10 bar of operation. So what ultrafiltration does, it separates macromolecules. And because of this, some of the materials can be deposited on the surface. However, there is no internal power plugging, thus it can be easily removed and reversible. So the cross-flow process is done for ultrafiltration. So ultrafiltration cannot be done using dead-end filtration. And we can use any membrane configuration. So for ultrafiltration, there is a recirculation for high total suspended solid feed. So for example, if the feed water contains a lot of solids, it may require several stages of ultrafiltration to achieve good permeate water. Backflushing can be done to loosen the fouling on top of the membrane surface. So a while ago, I mentioned that there is surface deposition, and backflushing can be used to remove this fouling. And this process is an excellent pretreatment for RO process. Now, let me proceed to nanofiltration. Nanofiltration removes molecules in the 0.001 micron range. So this is like ions or small molecules like sugars, salts, and slightly higher pressure from 0.5 to 6 megapascal, that's 5 to 60 bar. And this process forces water through the membrane. So this is essentially considered as a lower pressure version of reverse osmosis. And its performance characteristics is between reverse osmosis and ultrafiltration. So this process is the most widely applied filtration process for many applications because it only involves low pressure. So this can be applied for water softening, removal of organic matter, and desalting of organic reaction products. So our moderator, Dr. Titik Strokatun, she worked mainly on nanofiltration during her PhD work. And nanofiltration can be applied for cross-flow and transverse flow, and we can use any membrane configuration for this process. Lastly, we have reverse osmosis. So this is a process which involves applied pressure of more than 10 bar or 1 megapascal. So this is mainly used for desalination or the removal of salts in seawater and brackish water. So seawater, we know this is from the ocean. Brackish water is produced when seawater and fresh water, like from rivers, are mixed together. So that's brackish water. And this process uses spiral wound or hollow fiber membrane configuration. So basically, this is a huge process, and this can be applied using larger scale membranes. And the separation range is from 0.0001 to 0.001 micrometer. So this is very small, 0.1 nanometer to 1 nanometer. However, because of the small size of the membrane, larger size particles can easily deposit on top of the membrane surface. That is why pretreatment is necessary for this to be successful. So a while ago, it was mentioned that the other membrane processes like MF, UF, these can be considered as pretreatment processes for RO. And this is because without pretreatment, fouling will just occur. And this process is able to remove 95-99% of the total dissolved solids in the feed solution. Okay. Then what we can do using reverse osmosis is that we can concentrate the solution 50 to 25% less. So we can remove water, and the concentrated solution will have 4 to 6 times more than the concentration of the dissolved solid from the initial one. And this membrane is typically performed using a thin active layer, usually polyamide, and a porous support layer, typically polysulfone. So this membrane can be applied for various industries such as desalination, metal plating effluent treatment, color removal from textile effluents, and production of high purity water for different industries such as boiler feed, electronics, medical, and pharmaceutical applications. So typically, all over the world, RO or reverse osmosis is applied to produce fresh water from seawater. So currently, there are many seawater reverse osmosis or SWRO plants all over the world, typically in the Middle East. So if you know, if you're familiar with the Jubail seawater RO plant in Saudi Arabia, this uses reverse osmosis process for desalination, because we all know that the Middle East, there is a shortage of water because of its nature. So they have to develop desalination processes and remove salts from the seawater and produce fresh water. And this is also applied for many other countries as well. But the biggest challenge of reverse osmosis or RO is that it's quite expensive, because we have to apply a huge pressure to force water out of these membranes. And these spiral wound and hollow fiber membrane configurations are also quite costly. That's why the remaining RO plants that we have right now are mostly in Europe, Middle East, South Korea, Japan, and even these demonstrations are not very sustainable. So we still have to improve the whole process. Now, I have discussed MF, microfiltration, UF, ultrafiltration, NF, nanofiltration, RO, reverse osmosis. All of these are the pressure-driven membrane processes. So we need to apply pressure to treat the water. Now, let me introduce forward osmosis, which is a non-pressure driven membrane process. So this is a process which is driven by the osmotic pressure difference. So we have here two solutions, the feed solution and the draw solution. The feed solution contains lower concentration of solute. So typically this is fresh water from rivers. This is the membrane. And the draw solution is the one which has a higher concentration of solutes, typically seawater. So we know osmosis. Osmosis is the ability of water or the solvent to proceed from the side of lower concentration to higher concentration. So in this case, since water is mainly on this side and this has a lower concentration, we need the water needs to pass through the membrane towards the draw solution side like this. And this effectively dilutes the draw solution so that the concentration of the feed solution and the draw solution will be equal. So in this process, water transport happens across selectively the permeable membrane from the feed solution to the draw solution. And this has several advantages, like sustainable water recovery potential, because there is no applied pressure. This just happens naturally. And because there is no pressure application, there is low fouling tendency, there's low energy consumption, and it can also remove a huge number of contaminants, because the same membrane applied here is similar to the one applied for reverse osmosis, which is dense 0.01 nanometer range of membranes. And the FO process can be applied for desalination, resource recovery, solar power generation, and wastewater treatment. Why is this very attractive for wastewater treatment? It is because of its low fouling tendency. Okay, so now that I've introduced the membrane processes involved in wastewater treatment, here are the applications of membranes in wastewater treatment. So first, as I have already explained, the pressure-driven solid-liquid separation processes is the main application of membranes. So this is MF to remove the bacteria and large solids, UF to remove the colloids and to remove the larger size molecules, NF to remove the sugars, the salts, and RO or FO to RO, which is pressure driven. This removes most of the salt, and we are left with fresh, usable water. Next, tertiary treatment of wastewaters following secondary sedimentation. So one of the processes in wastewater treatment is sedimentation, or allowing the solids to deposit or to sediment below the feed. So wastewater treatment plants involve several processes, like first removing the big solids. So I don't know about Indonesia, but in the Philippines, where I am from, our wastewater is typically waste plus water. So you could see solid wastes coming from the houses, from companies, from factories, from offices. These are just thrown into the water. And this goes, all of this wastewater go directly to the wastewater treatment plant. And the first process is sedimentation, or the removal of all of these bigger sized particles, like the plastics, the food waste. All of these are first removed. Then the next process is secondary sedimentation, wherein they include some chemicals to further remove more waste. And we are left with a wastewater which is only containing the dissolved solids. And this is where membrane technology comes into play. So tertiary treatment. So after removing the bigger size particles, the bigger size waste, the wastewater is treated by membrane processes to remove the bacteria, the colloids, the suspended solids, etc. And membrane technology can also be used for production of high quality effluent in reuse schemes. So what this means is that, for example, we want to apply wastewater for, say, irrigation. So irrigation requires fresh water, but it doesn't necessarily have to be drinkable water, right? So what membrane technology can do is it can apply filtration and produce high quality effluent which can be reused for agriculture or for different processes, like right now agriculture is the most widely used application for the use of wastewater. And lastly, membrane technology can be used as an alternative for the sedimentation tank for solid and liquid separation in these processes. So as I earlier mentioned, most wastewater treatment plants use sedimentation tanks, which allow the deposition of solid wastes and allowing the water to just pass through. But if we have a bigger scale membrane technology process, we can eliminate the sedimentation tank and just apply filtration directly. But of course, this will be quite costly because we'll have to apply pressure, we'll have to get membranes, we'll have to have a huge capital cost. And this can be used for aerobic biological treatment and anaerobic biological treatment. So during my introduction about myself, my master's work sewage sludge. So sewage sludge contains several microorganisms which can be used for anaerobic and aerobic biological treatment, which can produce biofuels. So wastewater ultimately will be treated using biological processes so that we can get more materials, more useful resources from this waste. And how do we do that? We first treat the wastewater using membrane technology. Okay, so these are the applications of membranes in general water treatment, aside from wastewater recovery. Okay, first, desalination, or the removal of dissolved mineral salts in water. And this is mostly used to obtain fresh water from seawater. So this is usually done by nanofiltration and reverse osmosis. Next, stopping seawater intrusion. What is seawater intrusion? This is the movement of salt water into freshwater aquifers. Of course, these freshwater aquifers, this will be the one which goes into your tap. Drinking water, for laundry, for cleaning. And we don't want salt water to go through these freshwater aquifers because it will affect water quality. And this can lead to groundwater and freshwater quality degradation. So membrane processes can be used to stop seawater intrusion. Next, membrane process can also be used to treat brackish groundwater, or the groundwater which is slightly high salt concentration. It can also be used for water softening, or the removal of calcium, magnesium, and other metal cations in hard water. If you know, or if you notice, if you use water and soap and you don't wash it off, typically you will observe white stuff or scaling. So scaling happens because of the reaction of soap and the metal cations in hard water. And when we remove these cations in the water, this is the process known as water softening. And this will lessen the occurrence of water scaling. Next, membrane process can also be applied to remove the color, the odor, and other organic contaminants from water. And lastly, wastewater recovery can also be done for using membrane technology. Now, let me proceed to the next part. So, okay, we have now been introduced to the membrane processes. Now, let's go to the biological treatment with membrane separation. So this is a whole process which is typically done in wastewater treatment plants. Okay, first, we have the wastewater, the influent, which contains this much of biological oxygen demand. So this is the amount of organisms present in the wastewater. Suspended solids, total nitrogen, and phosphate. Okay, this wastewater goes through pretreatment. What could be the pretreatment? This is just the removal of the larger size plastics, larger size of the food waste, etc. Next, it goes to the sedimentary tank. So this sedimentation tank will produce primary sludge. Then, after this, it proceeds to the biological process, which uses the bacteria present in the sludge to produce methane, biogas, and other fuels. Lastly, it will have an effluent containing this some of a lower concentration of the bacteria, suspended solids, etc. And this will pass through microfiltration, which is a membrane process. And the final effluent will have very low biological oxygen demand. So it means that most of the organisms or the bacteria present in the wastewater eliminated. Suspended solids eliminated. And we will just be left with the concentrated secondary sludge. So this is a typical biological treatment with membrane separation process, which occurs in typical wastewater treatment plants. Now, I will introduce to you the membrane anaerobic reactor. So this anaerobic reactor contains bacteria, which are anaerobic. So anaerobic means there's no oxygen involved in this process. So what we get from this reactor is gas, methane, hydrogen. And so the wastewater influent goes into the reactor, wherein the bacteria present in this reactor digest the sludge, and we are left with the fuel. But this process will have a lot of waste, which can either be recycled or treated by a membrane technology process like UF or MF. And then the effluent can either be used for irrigation or for domestic use, and the concentrate will either be recycled or disposed. So this is again one of the applications of membrane technology in wastewater treatment. I am sure that in Indonesia, this is one of the main processes involved in wastewater treatment. Okay. So how do we dispose concentrated water? So in membrane technology, we are left with the effluent, which is the usable clean water, but we are also left with concentrated water, which contains a high amount of suspended solids and other waste. So typically, this is combined with reclaimed water and released to surface water. Previously, it was also injected into the deep well, but this is limited by geology. Some processes also involve evaporation and crystallization. So we just want to have solids and no liquids, but this is quite energy and cost intensive. Then some of the concentrated water was also used to irrigate golf courses and roadway vegetation, but this leads to more environmental concerns. Like definitely it will smell, definitely there's bacteria, definitely it's not clean. So people stopped doing this. And some of the concentrated water was also disposed in saline wetlands, but it's also limited by capacity. typically, we don't want to discharge wastewater back into the surface water. So what we are trying to do now is what we know as zero liquid discharge, wherein we use resource recovery as a feasible option to minimize waste disposal. So what is resource recovery? It is the removal and harnessing of reusable water, energy, biosolids, and other resources such as nutrients. So we have here the wastewater coming from the houses, the factories, and the industries, and it goes through the wastewater recovery facility, where inside there is membrane technology. And afterwards, after the membrane technology happened, we are left with concentrated waste. And from this waste, we can get water, we can get energy and biosolids from the sludge. This is already explained earlier from the anaerobic membrane process. And we can get phosphorus. Remember a while ago, our wastewater contains phosphate, and phosphate can be reduced into phosphorus, which can be used as fertilizer. So this is one of the these are some of the resources that we can get from wastewater. So resource recovery represents so from these sources of wastewater, we're able to get these resources, and then we can use this again and we can minimize our waste. And this will then be able to achieve what we know as circular economy. So these are some of the resources which can be recovered from wastewater after treatment. So we can get biogas, which can be used for energy, like heat and electricity. Then we have the nutrient-rich biosolids, which can be used for fertilizer in agriculture. And we have minerals, which can be recovered and used as fertilizer. So in addition to the environmental and health benefits of wastewater treatment, resource recovery also allows economic and financial benefits. So we can get more from our wastewater. And this is the concept that I have introduced earlier, which is known as circular economy, which is a model of production and consumption which involves recycling existing materials and products as long as possible. So this model extends the life cycle of products and aims to reduce the waste that we dispose into the environment. So this is different from linear economy. So our traditional economical model is linear, which means we have the natural resources, we make products, and we just turn this into waste and throw them away. And right now, landfills are everywhere, wastes are disposed into the oceans, and we don't want that anymore. We want to turn our waste into something more valuable. So the principle of circular economy is to eliminate waste and pollution and to circulate these products and materials and to regenerate this into nature. So we have here our raw materials. We're more concerned about water. So we design, we produce, we distribute, we consume, and then the waste that we get from consumption, we collect and we recycle. And we use them again. So finally, membrane technology is a promising solution to solve problems with wastewater. This technology can help us generate clean, usable water. It can also help us reduce our waste disposal and to recover our valuable resources from wastewater. Definitely, it's not a perfect process. There are still many challenges which need to be addressed, But definitely, it is not impossible to develop a sustainable membrane technology process for wastewater treatment. That's all. Thank you for your attention.
Thank you very much, Dr. Rao, for your informative and very interesting talk. Ladies and gentlemen, I hope you have already got many knowledge about membrane technology. And now we come to the question and answer session, and we still have a lot of time. Maybe you can deliver your question by unmute your microphone. Any question from participants? Yes. For Garnerita, please deliver your question by unmute your microphone.
Okay. Can you hear me, Mrs. Titik?
Yes, very clear.
Okay. Let me introduce myself. My name is Ganerita Ganesha Wardani. I'm college student of environmental engineering Diponegoro University. In Semarang, where Diponegoro University was located, the problem of seawater intrusion into the mainland is very large. Is the stopping seawater intrusion technology feasible to be applied in area? That's enough for me. Thank you.
Yes.
Okay. Thank you for your
Dr. Rao.
question. Okay, so as I earlier mentioned, definitely seawater intrusion is can be controlled or mitigated by membrane process. However, the main challenge is cost and infrastructure. Definitely, if we have the process, it can be used to stop seawater intrusion. But then to be able to do that, you need to have money, you need to have resources, you need to have a location to put your membrane plant. So yes, it is possible, but then this will only be possible if there are resources beforehand. Does that answer your question?
Hello?
Thank you for yes, thank you for the answer.
Okay. Thank you for the answer, Dr. Rao. Next, for the next question from Ms. Ariesta Sulistyo, please unmute your microphone.
Thank you for the opportunity. Let me introduce myself. I am Ariesta from Master Degree of Environmental Engineering di Diponegoro University. From the slide 15, you mentioned that there are 4 types of membranes. The first is microfiltration, and it can remove bacteria. And the second is ultrafiltration, nanofiltration for organic reaction product, and the last is reverse osmosis, and it's also can be used in medical field, right? So
Yes.
related to the coronavirus in water, which type of membrane could be remove the virus? And the second one, in the slide, but as we know, the problem in this problem is the sludge of the treatment is still big in a big size. So how do you think about it? Thank you very much.
Okay. Thank you for your questions. Okay. So regarding COVID in wastewater, actually this membrane, this virus can easily be removed by microfiltration or ultrafiltration membranes. But the thing is, the problem with the virus is that it still lives. So even if it's removed, it's still there. So what we need to do for the virus instead is to because what the membrane can do is just to separate, but not to disintegrate or to kill to kill the virus, right? So definitely in wastewater, if there's COVID-19 virus, it can be easily removed by membrane technology, but it's still there. It's still living. It's not actually not harmful. Okay. Then regarding your question on the sedimentation tank being replaced by membrane technology, yes, I agree that the sludge which is produced from either membrane technology or from sedimentation tank is huge. And that is why instead of the typical method of disposing the sludge, we are developing ways to generate resources or to recover resources from this sludge. And that is why after the sedimentation tank process or the membrane processes, we deliver the sludge into aerobic or anaerobic biological processes. And in this way, we can get more and we can use more of this sludge, which is typically just disposed. So instead of disposing this huge amount of sludge, then we have several processes which involve biological organisms or membrane process or both. So I did not include in my presentation that there are now biological processes which involve membranes. If like membrane bioreactor. And the membrane bioreactor typically uses forward osmosis, reverse osmosis type membranes. So in this case, the membrane bioreactor is able to use sludge, the wastewater, and it can generate, it can leave the water, it can allow the water to pass through the membrane. And we are left with a biological process inside wherein we can also get biogas or get other value added products. Actually, in South Korea, in the laboratory where I came from, they are now developing bioplastics from sludge. So this is another direction that the whole wastewater treatment is going to. So we are now starting to make bioproducts from wastewater. Does that answer your question?
Ms. Ariesta? Hello?
Thank you for the answer. It's very clear.
Okay, thank you. For next question, I got Mr. Ammar Sharaf from Yaman University. Mr. Ammar, can you hear my voice? Could you please deliver your question directly? Okay, maybe for because Mr. Ammar maybe cannot hear my voice, I will ask Mr. Musaid Ekman Bara. Yes, please deliver your question directly.
So, what are the main reasons led us to make the water treatment? And also that if we are finish for the treatment water, is that the permit in order to use for different activities?
Sorry. Can you please repeat the question?
Yes.
I said to you that what the main reasons that led us in order to make the water treatment, and if we are finished for the water treatment, that if that permit to use for different activities or not.
Maybe so the wastewater contain of different contaminant, and then how to differentiate or how to decide which membrane can be used for treat the different kind of wastewater. Is that your question? Yes, I think that is
So
the
sorry.
Dan banyak membantu petani-petani ikan juga.
Mr. Kurnia Putra, maybe. Yes, thank you. Yes, that is the question from Mr. Musaid Edman Bara. We have
Hello.
different kind of wastewater, and then we have different kind of membrane. How to decide which wastewater can be treated by which membrane?
Okay. Thank you. Thank you. Okay. If we have the wastewater and we characterize what is in the wastewater, we can easily see what are the components of the wastewater and what are the suitable processes involved. So I think definitely reverse osmosis is, since it's costly, it's not the most viable option. And it also depends on what application or what do you want to do with the wastewater. So if, for example, if you just want to get water which you can use for irrigation or for cleaning, maybe maximum nanofiltration would be enough. Because microfiltration, it just removes the bigger molecules. But then maybe these the smaller molecules will not be useful for your intended application. That's why you will need something like ultrafiltration or nanofiltration. So if I would think of an answer to the question, is that I think ultrafiltration should be a basic membrane process, because it is able to remove the same particles or same solutes as microfiltration, but it can also remove larger molecules, like other molecules like proteins. Nanofiltration in that case will require a higher energy, so it may be more energy intensive and more expensive also. So that is probably what I can say, that if you have wastewater, the first step will be ultrafiltration, should be. That will allow you to skip microfiltration and get water which is already usable, at least.
Thank you for your answer, Dr. Ralph. So maybe I can little bit add for make it more clear. So before we treat our wastewater, we have to know what kind of wastewater we have, what is inside the wastewater. After that, we know the type of membrane. which are microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, and then we can decide which one. And of course, we have to know what is our target. We want drinking water, we want irrigation water, or such kind of water. So we have to know firstly what kind of wastewater we want to treat, what kind of wastewater we want to treat. So we have to analyze first what is inside the wastewater we want to treat. So thank you very much for your clear answer, Dr. Ralph Gonzales. I hope that answer can satisfy Mr. Mosaid's question. And now I give time to Miss Sabrina. Please refer your question.
Okay, thank you for the. My name is Sabrina Sakila. I'm from undergraduate program Environmental Engineering. In slide 24, there is application of membranes in wastewater treatment. One of that is sedimentation tank. There are two ways: aerobic biological treatment and anaerobic biological treatment. What is the difference and what's better in terms of cost and practicality? Thank you.
Thank you.
For membrane, please answer the question, Dr. Ralph.
Yes, thank you. So the question is about which biological treatment is better, or are you asking about membrane process or sedimentation tank? I'm sorry.
More about sedimentation tank, like
Yes.
anaerobic and anaerobic.
I don't know. Sedimentation tank is a different process from the biological treatments. So, sorry, can I share my screen again?
Yes, yes, of course.
So in this slide, this is a sedimentation tank, and the biological process is the one that you were asking about. This biological process can either be aerobic or anaerobic. So sedimentation tank in this process is a pre-treatment for the biological process. So what I mentioned in that slide is that this sedimentation tank can be replaced by a membrane process. In terms of the biological process, anaerobic and aerobic biological process are very similar. It just depends on what kind of organisms there are. So aerobic process involves oxygen. So the bacteria that you need are different. Anaerobic one doesn't require oxygen. So the process is also different. The bacteria are also different. And because of that, the products are also different. So typically for anaerobic processes, we are left with methane, we are left with hydrogen, but for aerobic processes, we are usually left with carbon dioxide. So I cannot say actually which one is better. It just depends also on what you want to get and what you have to begin with. So, but in the case of sedimentation tank here, I can say that this can be eliminated as a pre-treatment for the wastewater prior to the biological process using membrane technology. So we can put MF and UF here, and we can proceed with the biological process. Does that answer your question?
Sabrina, is that satisfy your question?
Yes,
So
thank you.
actually, sedimentation is only physical process, and then biological process is biological process. So that is from that slide is before microfiltration. But if we use integrated membrane process, that process can be cut. So we can remove that process and use membrane process instead. Thank you for your question. Dr. Gonzales, actually there is a question that sent to me from Amar Saraf from Yemen.
Yes.
He asked about evaporation. Evaporation is one way to dispose contaminated water, but
Yes.
the evaporation process will remain much older. How we can remove it? Thank you. And this is not about membrane, this is about evaporation that you little bit mentioned in your presentation.
Yes. So evaporation can be used to so if we use evaporation for the concentrated water, then we remove all the liquids. So the odor definitely remains. And that is why this solid remaining can be used for other applications. So as I mentioned during the circular economy resource recovery slides, that this can be used for say manure or concentrated solids from wastewater can be used for fertilizer, for example, or this can be applied for biosolids. So this is actually out of the membrane scope, but right now scientists are all thinking of what to do with waste, and we are developing different products. Odor will remain, but then odor can be easily removed if we kill the bacteria producing the odor. So odor can be easily controlled by disinfection and by removal of the odor producing bacteria. So I think that answers the question. And what we do with solids remaining after evaporation, that's for scientists to know. They're currently discovering ways to use this and to create something out of it.
Okay, thank you for your clear answer. I think we still have time. I think your presentation is very interesting. That's why there are so many questions. Is that okay, Dr. Ralph?
Yes, of course.
Yes, okay, thank you. For Miss Salistia, please.
Mr. Bu.
Sorry. I'm so sorry. Okay, Mr. Salistia, please.
Okay, Assalamualaikum. Thank you very much. My name is Salistia. I have experience on distillation using membrane. The main issue is the high cost due to fixed cost material, especially for membrane and the lifetime. I think I want to ask Mr. Dr. Gonzales how to improve this issue to make membrane more economically. Moreover, this is for wastewater treatment. As we know, in industrial wastewater treatment is all more economically than conventional. I think that's.
Mr. Salistia from industry, sorry.
Yes, I am from industry.
Okay.
Okay, so I wasn't able to catch the second question, but I will first answer the first question. So membrane cost is actually not that high. What is actually more expensive is the process. So there are currently many commercially available membranes, and because the market is already very competitive, it has become quite economical compared to previous years. So what I can say is these companies will all find a way to make their membranes cheaper and more sustainable. But the bigger issue here for application of membranes in terms of cost is the capital cost or the infrastructure. You first, if you want a large scale membrane technology process, you need to find a place. Then you need to build the plant. Then, of course, in such ways, you don't only use one membrane. You use several membranes. So even if the unit cost of membrane is cheaper than it used to be, compounding all of these materials, all of this labor is also expensive. Electricity is also expensive. And this affect the cost and the sustainability of membrane processes. Lifetime also is now becoming better and better for each generation of membranes. So previously, membranes are easily fouled and they are not able to be used for a long time. But currently, simple backflushing or simple air scoring can be done, and the membranes can be regenerated and be used again for several cycles. So currently, for membranes in commercially available membranes, have a lifetime of 5 to 10 years or even longer than that. So that means the membranes are not the problem. The membrane is that we need to maintain the membrane treatment plant. And the plant itself is more costly than the membrane itself. We need to find someone to maintain. We need to constantly check for if the efficiency of the filtration is similar. We need to check for the growth of bacteria, for example, on the walls of the filtration tank. These are several issues that we need to address. So if you're familiar with the economical analysis done on membrane processes, like capital expenses, operation expenses, the biggest operation expense and capital expense is on the infrastructure, on the construction of the membrane plant rather than the membrane itself. So that is the biggest challenge for in terms of cost for industrial application of membrane technology. Now, I would like to know what the second question is again. I'm sorry.
The second is how to improve the cost. For example, how to make the material membranes more cheaply, more cheap.
Yes. Thank you for your question. One of the ways that we do that is to use natural products. So one of the most commonly membranes are made from polymer, and polymer is, since it's synthetic, it's expensive. But natural products can also be used to prepare membranes. And why is that so? Because one of the membrane materials that we have used for a long time now is cellulose. And cellulose is present in agricultural byproducts, in food, and in residues from environment. And using these natural products that we can get, we can extract the cellulose, and we can use the cellulose for to develop membranes. But then this will require a longer time for optimization, for a larger scale development. But this is a step that we can do to decrease the cost of membrane development and membrane processes. So in terms of membranes, I think the biggest way that we can do is, again, use reuse wastes. So we can get cellulose from agricultural waste and make it into membrane and use it for membrane processes. But then the bigger issue here for the membrane process is the cost of the construction and the cost of operation. And this is not something that we can control, especially now that global oil prices are increasing. Definitely electricity is also increasing. And this is not something that we can control. Thus, I cannot find any answer to how to make this cheaper. But hopefully the world situation will subside, and we can go back to having cheaper electricity or cheaper power costs. And in that way, we can get a cheaper membrane process in the future. If you can also find a more sustainable energy source, that would be better. But then these processes are also in the earlier stages. So definitely we can generate biofuel, biogas, and use this as power source. But then this is just 1% of what we need, and it's not enough.
Thank you for your answer, Dr. Ralph Gonzales. For Mr. Salistia, mungkin I think it is common for us that live in developing country that we always reject or have we don't want to change our technology, but in fact, in some arid country like in Middle East, they use membrane technology, and even though the first time they think membrane technology also expensive compared to traditional technology. And we know also in developed countries such as Korea, US, and then Japan, and also our neighbor Singapore, they use membrane technology also for treating wastewater, for producing their drinking water, because Singapore, we know they don't have any water source. That's why they have to use advanced technology for producing drinking water for themselves. But yeah, for membrane technology, the big challenges is the first installment, I think. The first installation is very expensive, but after that, if we maintain the process regularly, it will decrease much cost that compared to the traditional. Question. Ms. Tari, could you please deliver your question directly?
Hello, good morning, Mr. Gonzales.
Yes.
Okay, sorry.
You are from company or from master?
Yeah, I'm from company. I'm not I'm not a student.
Yes.
So I'm interested to know the common practice that industry usually do to the reject water of wastewater, from RO, from reverse osmosis. What do they usually do? Because here we don't have the regulation of reject water yet, so that the industry tend to just throw it back to the sea, which is very harmful actually for the corals reef. Yeah, I mean, yeah, for the marine life in general. And then the second one is that you mentioned about nutrient recovery, and for me it's not really clear about the topic here, because nutrient is actually very fast. We can talk about nitrogen or phosphorus, and so what is it actually, and what methods that they usually do to the specific nutrient that here that is mentioned? Thank you.
Okay. Thank you for your questions. So first, industries and membrane processes are usually regulated by the government or by the governing bodies. So for example, if you mentioned that there's no standard on how much we can throw into the bodies of water, then this cannot be regulated. But what I know is that for industries is that at least here in Japan, industries are working with membrane technology, because here there's a very strict regulation on how much oil, how much total suspended solids, or even the nitrogen content, phosphorus content that you can deliver into the water bodies. So the membrane technology that you need for that is dependent on what you want to remove, right? So for example, if an industrial company produces oily wastewater, then they have to develop a process which will allow them to separate water and oil before they dispose the water, right? So in that case, if one industry is producing a nitrogen-rich wastewater, then what they need to do is to remove the nitrogen using, say, reverse osmosis. So I think in that case, the answer is still, you should know what is in the wastewater before deciding what type of process or what type of membrane you need to treat it.
Sorry,
And
may I
yes.
interrupt? I'm afraid because of the time, so I think I need to interrupt. I'm sorry about my question is unclear. So actually, my question is about what do industry usually do to the of reverse osmosis here is for the salination.
Yes.
Meaning that the reject water will have high salinity, which is harmful to the marine life.
Yes.
So yeah, so the wastewater is, so the reject do they usually do to the reject water? Thank you.
So as I earlier mentioned, we can integrate membrane processes into other processes. Other things that we of a high salinity wastewater can be used as a draw solution for forward osmosis, for example. And in this case, there are several studies conducted on using high salinity wastewater energy generation. So that's one thing. There are already processes in place wherein the rejected water or the concentrated water can be used for other processes. So it's not exactly a simple process. Like I think what membrane technology is actually promising is it can be integrated with several other processes, and it can be integrated and it can be used for different applications. So it can be a pretreatment, it can be the final stage treatment procedure. But what is important here is that you are able to get something useful. So if the reject water contains high salinity, is produced from membrane technology, then there can still be other technologies. Some may be membrane, some may be not, which can use this high salinity wastewater for their own purpose. So I am not actually familiar with how industries actually act because I have never been in an industry. But what I can say is that the disposal performed by industries should be regulated by the government. So if their wastewater is above these standards, then they should use technology to treat this prior to disposal. And the process may vary from each wastewater because again, it depends on what is there and what is not. Okay. Then the second question, sorry, could you repeat the second question?
Specification of the nutrient that we can recover from membrane technology.
Here's the thing. The nutrients in wastewater vary from what kind of wastewater, even from which industry produced the wastewater. So the wastewater from the houses, that's different from the wastewater from the companies and from agriculture. So ultimately, what we know is that wastewater contains phosphorus. It contains ions. There will be sodium, there will be calcium, there will be nitrogen. And I did not go deeper into this because it's a different presentation on its own. Because I think it will be much be longer than the actual presentation if I included what kind of nutrients we can recover from wastewater. But definitely, whatever is in the wastewater can be recovered and can be used for other purposes. So, for example, if it's a phosphorus-rich wastewater, the phosphorus can be recovered, and then it can be used as fertilizer. Same with nitrogen. Same with potassium. How if the wastewater contains a lot of sodium and magnesium or lithium, we can get the lithium and use this for lithium-ion batteries, right? So there are many ways in which we can use the resources in the wastewater. Not necessarily, there's no singular answer to this question. Yes, so that's why it's a different. If I will do this presentation again, if Diponegoro University will invite me again, maybe I will talk next time about resource recovery, right? Because it's a more exciting topic than say because there are many resources which we can get from our wastewaters.
Yeah. Thank you for your clear answer, Dr. Gonzales. Actually, in Japan, it's almost lunchtime, but still there is a participant who wants to ask a question. Do you still have time to answer or energy maybe for answering the question?
Yes, maybe 1 or 2 questions.
Okay, please, Miss Saima Lashari, please deliver your question.
Thank you. Thanks for your time. And it's really interesting topic. But I have a question to ask that earlier you have mentioned that the process itself is not much more complicated or much more highly cost. So if in some areas, such as I'm living in that areas, and there is a need to install or establish a plant for the wastewater treatment. So if someone wants to do that in future, so which community is responsible for that, for the plantations or for the industries to stabilize? Are the government or any other research or scientific communities responsible to establish the industry or plantation for treatment of wastewater?
Thank you for your question. That's actually interesting. To be honest, in the Philippines, we don't have a wastewater treatment plant. Why? Because there is no support from the government. Again, wastewater treatment is it's an effort of community, government, industrial partners, and universities. The brain power should be focused from the universities and the government scientists. That should be the primary brain power. But then the brain power cannot do anything if there is no money, if there is no support available. And we can do experiments in the laboratory, but this is not actually useful until we apply it for a bigger scale. And in that case, that's where industries and the government will have to go in. And I think there is no singular entity or no singular group responsible for this. It should be a collaboration between the university, the academe, the industry, and the governing body. Because as I earlier mentioned, it's costly. And the results are not just for a single person or for one group of people. If you maintain a large wastewater treatment plant which can treat wastewater, it will benefit maybe a whole city or a whole region. So this requires support from the government, for example. So I'm not sure if that answered your question.
Thank you. Thank you so much. It means the government and universities and scientific research communities are responsible, and we can do, a single person can do nothing without their support.
Yes, and I would also like to add, industries should be responsible also, because industries contribute to a lot of the waste that we throw into the water bodies. So I think government is responsible because of the domestic wastewater produced from houses and everything, but industrial wastewater is actually more harmful. That's why it is their corporate social responsibility to be involved in wastewater treatment. And also they have more money.
Thank you. Thank you so much.
Thank you very much for your question and thank you very much for your answer, Dr. Gonzales. Okay, maybe due to the limited time, we do apologize that maybe we cannot answer all of the questions if there are still questions from the participants. However, we understand that the question it will be become our concern. And I think this is the end of the question and answer session. I do hope all questions have been answered clearly. And thank you to all participants for actively participate to this lecture. And I think I will give the time back to MC. Thank you very much, Dr. Gonzales, Dr. Ralph Gonzales. Very nice to meet you virtually. Usually we have lunch together with our lab mates, but now we are separated by millions kilometers distance. Thank you very much. I hope we can have another chance to have a scientific talk. And for the distinguished participants, I do thank for your active participation, and I hope we can maintain this good relationship in the future. I give the time to the MC. Thank you very much.
Okay, thank you, Mrs. Titi. Okay, everyone. Firstly, I would like to express my gratitude for Dr. Rafael Gonzalez for the presentation, the lecture, and the clear and helpful answer for all of the questions. It's an honor to have you, and it was a very insightful session. As an environmental engineering student, actually, I gained immense knowledge that valuable for my career later on. And I believe anyone on this meeting which have different background, whether have environmental background or only have a huge interest in it, find the seminar so beneficial and worthwhile for each one of them. In order to express our gratitude on behalf of all of the committees, we have a certificate for you, and I would like the operator to share screen. All right, here we would like to express our gratitude for Dr. Rafael Gonzalez. Here's the certificate. I hope you had great time as well, because we all here absolutely did. Thank you once again, Dr. Gonzalez.
Thank you.
Okay, for the next session, everyone, I would like also express my gratitude to Mrs. Titi for guiding the session. Thanks to you, I really enjoyed the seminar, and I believe everyone in this room feel the same too. Okay, here's the certificate, Mrs. Titi. I hope you enjoyed the time as well. Thank you so much.
Thank you very much. There is a photo session, right?
All right, after this, we will have the photo session. Okay, everyone, before we will move on to the photo session, I also would like to remind and inform all of the participants who wonder whether the source of material is okay to being shared or not. It is actually has been sent in the WhatsApp group of participants, so kindly check it there, you'll find it. Now we are coming to the end of the event. Before I close the session in formal way, I would like every participant to turn the camera feature on so we could take several pictures for the documentation. I will wait in several times, so you will have time to turn your camera feature on. Okay, since some of you here have turned the camera feature on, I will lead the documentation session. And 1, 2, 3. Okay, once again, 1, 2, 3. Okay, thank you for your time. It has been an enjoyable experience for every one of us, I bet. Okay, we really come to the end of this session. So I am Adila on behalf of all of the committees. I would like to say thank you to all of the participants for your enthusiasm and participation. I really appreciate it. And I hope we have another great opportunity so we could have, another discussion as well. And as you can see in the chat box is the evaluation link in the chat box below that have been sent from our committees. So it will be great for us if you spare a little time to fill it. And also you can see in the screen, we have also the barcode. You could kindly scan it, or you could type the link of the evaluation. And also for those of you who doesn't feel the presency link yet, you could fill the link also. It will be great for us if you spare a little time to fill it. So thank you very much, everyone. And see you on another international lecture series by the Department of Environmental Engineering di Diponegoro University. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Adila. Good luck for your ISMA program in Netherlands.
Actually, in Hungary.
Sorry?
In Hungary.
Hungary?
Yeah.
Hungaria.
Ya, di Hungaria, Bu Titi.
Ungar.
Ungar.
Ungar. So close with Semarang. Okay.
Thank you everyone. Terima kasih semuanya.
Thank you Pak Darno.
Yeah, see you next international guest lecture.
Okay. Thank you, Ralph.